In this video, I'm going to be specifically taking a look at an AP Calculus AB question that generally deals with a Riemann sum, and they have given you a table of values. Alright, this is a pretty common open-ended question, and while there usually is a part A, B, C, and D, we are going to only focus on just this one specific question because it deals with the Riemann sum and I'm given the table. Alright, so in this question here, I've got this table. It says that rocket A has a positive velocity v of t. Alright, so they've given me values for my velocity function. After being launched upward from an initial height of 0 feet at time t equals 0 seconds, the velocity of the rocket is recorded at selected values of t over the interval from 0 to 80 seconds, as shown in the table. Alright, now what they want us to do, they want us to do, using correct units, explain the meaning of the integral from 10 to 70 of vt dt in terms of the rocket's flight. Use a midpoint Riemann sum with 3 subintervals of equal length to approximate that integral from 0 to 70 of vt dt. Alright, now let's first of all talk about the meaning of what this integral is here. Okay? And we're integrating the velocity function. If you go back and you remember, here let's even write this down. Let's see. When you first were introduced into the position function, the velocity function, and the acceleration function, all right, you were generally probably given the position function, and then you took the derivative of that, and then that gave you the velocity function, and you took the derivative of that and got the acceleration function. Okay, that's reviewing. Probably back really early into your derivatives. Okay, now if we recall, when we integrate a function, if we integrate the derivative, it gives us back the original function because it's undoing that derivative notation. So if I'm integrating the velocity, which is the derivative of the position function, okay, so when I integrate it, then I am going to then get back that original position function. Alright, so then what this tells me in terms of the rocket's flight, it's going to represent the distance, in this particular scenario in feet, traveled by the rocket from 10 to 70, from 10 seconds to 70 seconds. Alright, so that's your thinking process of how you're going to do that, and then when we get at the very end, then we will actually write that down at the end. We'll summarize that at the end. It says using a midpoint Riemann sum of 3 equal subintervals. Okay, so that's important here. So midpoint Riemann sum, 3 subintervals of equal length, and then we're going to approximate that integral. Alright, so that's what I'm going to focus on first, and then we'll write the meaning at the end. Alright, so let's pull that up so that we can still look at it. Okay, so I know that I need to approximate this integral, so I'm going to integrate from 10 to 70 of vt dt. Alright, now I'm going to come up here. Now, since I don't have my function, alright, all I have is a table of values, then I've got to analyze what's going on in this table of values. Okay, so I'm running from 10 to 70. So really, I don't need the entire chart. I don't need this. Alright, and I don't need this, because I'm only running from 10 to 70. Okay, now you've got to think of, okay, I'm going to divide this into 3 equal subintervals. So I need to take these values and divide into 3 equal subintervals. Alright, and since I'm doing a midpoint Riemann sum, alright, then that kind of tells me that I'm going to have to group these in 3s because I need a midpoint, and I need to be able to know the value of that midpoint because an integral, you need to be thinking length times width of each one of the rectangles or each one of these subintervals that you're going to be adding up. Okay, so for my first interval, I could do, if I go from 10 to 30, alright, that's going to give me a width equal to 20. From 10 to 30 is 20. Alright, and I would clearly have a midpoint in there that I could easily find. Alright, now if I have to keep all intervals of 20, width of 20, then coming over here, if I did this 50 to 70, then that means my middle one's going to have to be in here from like 30 to 50. That could be my second interval, so that definitely is a width of 20. All right, and then a third interval there of 50 to 70. All right, and it'll take some practice getting how you can figure out, 3 intervals of equal length. It will take some practice there. All right, now that first interval, let's see here. I did that in orange, so let's do that. All right, now I need the width, which we know is 20. All right, and then I need height, because I need length times width, length times width, length times width of each one of these intervals, and I'm going to add them up. So the width of my first interval there is 20. All right, now if I'm going to use a midpoint Riemann sum, here's my midpoint. Okay, this right here is my midpoint. All right, and how high did it go? Well, when I plugged in 20, then my v of t is 22. So it went a height of 22. There's how tall it is. All right, so width times how tall that rectangle is. Okay, and then now let's do the second one. All right, again, it has a width of 20. Now how high it is. Okay, so here's my width of 20. All right, I need a midpoint Riemann sum, so here's my midpoint Riemann sum. When I plug in 40 into my v of t, I get out a 35, so I've got a height of 35. Okay, and then for my last rectangle, again, it's going to be a width of 20. All right, and then how high? Well, midpoint Riemann sum, so I'm going to come to the middle of that interval. Right here, I plug in 60, I get out a 44. Okay, so then I can estimate my Riemann sum there by multiplying here. I think I get a 440. Multiplying here, I get a 700. Multiplying here, I get an 880, which is going to give me roughly 2,020 feet there. Okay, so there is me estimating, approximating the integral from 10 to 70 of vt dt using that table of values. All right, now I need to write using correct units. There was my correct units. Explain the meaning of that. Okay, now it did say at the very beginning here, rocket A has a positive velocity, so it wouldn't hurt you at all to go ahead and put that in your explanation. Okay, so let's say since velocity is positive, the integral from 10 to 70 of vt dt represents, we talked about this at the very beginning of the video, the distance. All right, now on the AP test, they're going to definitely want the units indicated. All right, so it's representing the distance in feet, because this was feet per second for my velocity, so that means my position function would be measured in feet. So in feet traveled by rocket A from, now you're going to want to definitely indicate that this integral is going from 10 to 70. Well, so what is that 10 and 70? It's time. So t equal 10 seconds to 70 seconds. All right, indicating t equals there. All right, so a really good explanation of the meaning of that. You're definitely going to want to indicate the integral in your answer. You're going to want to know that it's you're going to want to indicate that the distance is in feet. All right, the AP people are going to look for, did you indicate the label of that? All right, and then indicating those limits of integration. What do they mean specifically? T equals 10 seconds to 70 seconds. And you could even do a T equals, actually probably be a good, put T equal 10 seconds to T equals 70 seconds. All right. So just one specific example using a Riemann sum with your table of values, how you've got to go through it, come up with your meaning, and then approximate that integral. Definitely thanks for watching, and be sure and subscribe to the channel. Thanks.